Thank you, Sarah. Thank you for inviting me today. It's interesting. I've been here for just a year, enjoyed my time here quite a lot. And today, the other day when I got this email about giving a talk. So normally when I'm out there giving a talk, most of it is the research that I do, so a bunch of equation, and 10% of it is what it means to the general audience. And so this was going to be flip. So it was interesting while I was trying to think about what to say. And I would like to thank you for inviting me because it gave me the opportunity to think about what it means, what I do, what is the relevance of it in the broader realm of things. So overall, my area of expertise is in the domain of water. I'm interested in different kinds of water issues around the world. So just to give you an idea, sanitation and access to clean water, maintaining aquatic ecosystem services, floods, food, water pollution. So I teach a water resource sustainability class this semester. It's a graduate level class where we talk of water issues around the world. My particular expertise is in the domain of water quality, water pollution. So basically to figure out how water flows over the landscape. And when it flows over the landscape, you have humans contributing different kinds of waste to the water. What is the chemistry of the processes happening within the water and what it contributes to downstream, as in Gulf of Mexico, hypoxia, and things like that. So I'll explain my title at the end. For now, let me say that my interest right now here is to look at water quality in the Mississippi Basin. The Mississippi Basin drains about 41% of the US, so that the colored area over here is the Mississippi Basin. And one of the big issues of the Mississippi Basin is that it has contributed to hypoxia in the Gulf of Mexico. Hypoxia is not unique to the Mississippi Basin. If you look at all the red dots in this figure, all of these are hypoxic regions around the world. So look how the east coast of US is. Look at Europe. So hypoxia is a pretty serious problem. And hypoxia, by definition, is a condition when oxygen concentrations in the water is less than 2 milligrams per liter. And so this is the number of hypoxic sites in the world. So hypoxia in 1900s was very, very low. And look at the rate of increase in hypoxic sites around the world. So this is a pretty serious problem and increasing at a very, very fast rate. So what contributes to hypoxia? Well, we do. So this is an interesting figure. I apologize for the poor quality of it. This is what I got. So the black dots are still the hypoxic regions around the world. And green indicates that there is low human footprint, low population density. And the redder the areas go, there is more population density. So you see how population density correlates with hypoxic regions? So it is all a part of humans changing the ecosystem. So what is hypoxia? What does hypoxia do to the system? Well, that is captured very well by this one sentence, right? It's breathing of the ecosystem. So a little bit more. So when you have hypoxia, when you have low oxygen concentrations, your benthic organisms die because they can't move away. So benthic organisms are those that live at the bottom of the ocean or the lake. So they die. The fish, sometimes they die. Sometimes if they can migrate away, they migrate away. Their food resource is taken up, so they migrate away or die. Effect on humans? Well, fisheries are affected, tourism is affected. So this a lot of you might be familiar with it, but I'll just go over it briefly. What causes hypoxia? So here you have fresh river water that brings in a lot of nutrients. And because this water is fresh water as opposed to the salt water of the ocean, it floats on top of the seawater. Plus, this water is also warmer. So you have these two layers, the top layer which is lighter, warmer river water, and the bottom layer which is denser, saltier seawater. Now, when this fresh water brings in a lot of nutrients, what it simulates is a lot of growth of phytoplankton in this top layer. The phytoplankton then die and they sink to the bottom of the ocean. When they sink to the bottom of the ocean, there's degraded decomposers which decompose this phytoplankton, and in the process they consume a lot of oxygen, which creates this anoxic or hypoxic zones in the bottom of the ocean. When you have hypoxia, some of the fish live, whereas the bottom of the ocean, the benthic organisms die. So what causes hypoxia? Large amounts of nitrogen loads to the Gulf causes hypoxia. So I found this interesting. I was reading this article the other day about an Iowa farmer talking about the fact that less than 4 decades ago, when he remembers his father growing corn and fertilizers first coming into play in a very, very strong way, how fast the corn grew and what a big deal it was. And we can trace back that story to the 1900s when first ammonia was synthesized by the Haber-Bosch process. What that brought in was this huge green revolution, large increase in agricultural lands all over the earth, and world hunger was reduced to a large extent. So that is the benefit of synthesis of fertilizer. What came as a repercussion is hypoxia. So what you see over here on the x-axis is 1900 to 2000. And on the y-axis you see mass of nitrogen, right? So if you look here, if you look at this line in here, this is industrially fixed nitrogen that is added to the system. And the red line here is the number of hypoxic sites. So you see how these two are correlated. So increase in nitrogen in the world resulted directly to increase in the hypoxic sites in the world. So a brief about what happens when fertilizers are applied to the soil. So here, this is fertilizers being applied to the soil. And within the soil, you have this complex set of processes. And I'm not going to go into the details of the processes, but I just wanted to appreciate the fact that it's not simple to go out and figure what happens in each of these stages and the fertilizer that you're applying, which pathway it takes. But it's kind of known that some of it leaches to the surface water, some of it leaches to the groundwater, and some of it leaches to the deep, deep groundwater and travels very long distances. So this is a figure of the Mississippi Basin with the total loads of nitrogen. So here you see this very dark region is which contributes most amount of nitrogen for the Gulf of Mexico hypoxia. And this is the corn soybean belt, right? This is kind of known also that this is the main contributor. And the phosphorus is also kind of similar. The phosphorus pattern is kind of similar. So here, this is a picture of how nitrogen loads. We saw that more on an overall world basis. This is just the Gulf of Mexico. So here you see the hypoxic zone size and how that relates to the nitrate load. So the open circles in that figure is the nitrogen loading in the month of May, and the closed circle, the filled circles there are the size of the hypoxic zone. So you see in years you have large nitrogen loading, you have a large hypoxic zone. So it's very directly correlated. The other thing, notice the months. So it says nitrogen loading in the month of May and hypoxic zone in the month of July. So why is that so? Well, there is a time lag. You have most of the nitrogen that comes off your field comes in May, June. And then the plankton grow and they die. So that cycle robs the ocean of its oxygen. So that is the time lag between these processes. And by September, the hypoxic zone kind of goes away because what you have is these storms come in and they mix up the water. So then you have oxygen from the atmosphere mixing the bottom layer, so the hypoxia kind of disappears. So this again is a picture of years along the x-axis and area of the hypoxic zone, and you see that it's steadily increasing. Again, you see these cycles, and the reason you see these cycles are these are kind of the natural cycles that you see in the stream flow. So stream flow is not constant from year to year. You have these cycles, and the hypoxic zone cycles kind of follow that pattern. So the red line, the top red line, is more or less an average of the area over these last 10, 20 years. And the red line here is the action plan. So there was a huge amount of work done on Mississippi Basin action plan, figuring out how much do you need the hypoxic zone to be reduced. So this was the set target, 2,000 square miles. And some amount of models that were built and calculations that was done said that fertilizer applications need to be reduced by 50% to achieve that. So before we go further into this, I wanted to talk about this one point, is that this problem, this hypoxia or any water quality problem, it's not purely a science problem, because you can do all the kinds of models that you like, but ultimately it hinges on linking water quality, water quantity to the socioeconomics of the system, because if you say fertilizer application reduced by 50%, it's not going to be implemented, and so that's what has happened for a lot of time. But in order to design effective management strategies, you need to figure out how what you are doing at the scale of a single farm relates to what's happening at the Gulf of Mexico. Now that's the part that gets really, really tough. The reason it gets tough is because you need to figure out what is happening across scales. So here I said, from the scale of a tile, a single tile drain, to the scale of the tide or the Mississippi Basin, you need to go across scales. So it is easy to figure out, and a lot of people have done work on what is happening at the scale of like a small soil block, all the processes that are happening. But each soil block is different. So how do you know what are the properties in each soil block? Then how do you know what is the property across the catchment? So that is the question that is really challenging. Now, the way this is done, the kind of approach that's normally taken to do this, is that this is a watershed. And normally what we do is we sit at the watershed outlet and we measure hydrographs and chemographs. So what that is we measure water quality with time, and we measure the flow that is going past this one point with time, right? And then we divide this area into these small units, right? This is one unit. And in this unit, all these complex processes have to be described. Now, think about the watershed made up of a zillion of these units. And in each unit, you need to know what the rates of each of these processes are, what the masses are in the system. So it becomes often an unsolvable problem. The way you get past it is that you kind of put some parameters in this box, and then you say this box is similar to a couple more other boxes. So you have a model with about 20 or 30 parameters, and then you go in and tune those parameters so that you get this output. Now you can immediately guess that if you are tuning 30 things to get one number, you can tune it any different ways, and you would get the same number. So that in our world is called the concept of equifinality or non-uniqueness, non-unique parameters. And then when you use those parameters to say what will happen when farmer A, who lives here, does something at the watershed outlet, you're not really very accurate. And it has been observed, so since the hypoxic zone problem became a huge deal, there's a number of things going on, like conservation reserve programs, so a number of activities going on. The main challenge being, a lot of times you see land use change happening, but when do we see the benefit of the land use change? Don't really know, because there is a time lag and it's difficult to quantify. So this challenge. So we propose, so this is now I'm moving into more my area of research. What I'm interested in is building a different group of models, different kind of models. And this is called kind of the pattern-based model. So there's a group of us who are interested in this kind of a model. So what is this? So the idea is this. We know that we know the physics of what's happening at the scale of a single soil block. But we also know that it's very difficult to go up the scale. So this is called a bottom-up approach. So you start at the small scale and you build your way up. The other way is you start at the large scale and then you kind of narrow your way down. So that's called the top-down approach. And what we say is you need to be doing both. You need to understand the mechanics of the scale, but then you need to be looking at the larger picture and say what is important. So I'll give you the examples in a bit. So the pattern-based approach is based on the 4 P's. The first P is, of course, patterns. So we look across landscapes and we search for patterns in the landscape. And then we say, well, what are the processes that contribute to that pattern? Say, for example, flow through the tile drain may be a process. We know that there are zillion processes going on in nature, but maybe one of them is the main cause of the pattern that we see. So we kind of work our way backwards to say what is the process that's causing this pattern. And then once we kind of have an idea of the process, we say, well, now we have this entire domain of models that describe all the processes in detail. Which of the processes can we take away? Because it may be not that important. So then we go into the prediction mode. And all of this is tied together by the idea of purpose. We need to, whenever we are building a model, it's necessary that we keep in mind the purpose of the model. As an example, if you're thinking about hypoxia in the Gulf of Mexico, you need to only know maybe monthly loads of nitrogen. That's enough to predict what kind of hypoxic processes would happen. However, if you're thinking of predicting something like a chronic or an acute toxicity to fish, so some discharge of some chemical that causes an acute toxicity, you would need to know a daily concentration or even an hourly concentration. So the model that you would need for both these problems, conventionally it's the same model is used with just different parameters. What we are saying is that you need to be thinking maybe of different models. When you're talking about Gulf of Mexico, you're integrating over this large million square kilometer Mississippi basin, right? So in that case scale, when you're talking about time, you can maybe do a month and be okay. When you're talking about what's happening in the stream over here, you need to maybe be thinking about a different kind of time scale. So depending upon what your interest is, you build your model. So patterns, we start our journey with patterns. Patterns offer a window into landscape processes and they help us build hypotheses. We start out by asking what are the emergent patterns in a landscape. When I say emergent patterns, what I'm talking of is a pattern that's not immediately obvious when you are looking at the small scale processes, but at the large scale you see it emerging. Like a river network, that's an emergent pattern. It has similarity to a tree network, a tree branching. So those are, nature has some amazing things and we learn from it. And then we use that knowledge to create models. So let me give you an example of one of these cases. This is what we did. So when you have rain falling over your watershed, so this is my cartoon watershed and I have the rain falling over that watershed. And I'm interested in understanding what is the stream flow. So I want to convert my rainfall and want to predict stream flow. Now in a conventional model to do that, this is tough because when the rain falls on the surface, it can go through different ways. It can go on top, it can leach down, it can flow through the subsurface. There can be different times taken to travel depending upon the particular geology. And so it's very difficult to go from here, the rainfall, to predict what the stream flow is. But now think about the Midwestern catchments. Think back to when the first settlers came in. You had these landscapes made of wetlands, right? And what they wanted to do was use this for farming. So they wanted to drain these wetlands. The way they did it is that they placed these tile drains, which are these pipes, about a meter or so below the ground surface. So what happens is that when you have rainfall, it goes to these tile drains, and then there's a lot of tile drains all over your watershed, so it flows fast through the tile drains into your stream. So your land remains dry and can be used for agriculture. So basically they created a man-made artificial network that bypasses the complexity, the fascinating complexity of the landscape. So in terms of nitrogen loads, it makes the problem severe because you're not giving it time to react in the landscape. In terms of a modeler's view, it makes the problem simpler. You don't need to consider all this complexity. It's simple. It flows, and it flows through the tile network. It's easier to model it because it's just a pipe network. So thus our hypothesis was that human modification of this particular watershed is actually making it simpler to model. And because of our mindset of always wanted to build a complex model, we've not used it adequately, this attribute of this watershed. So this is an example of that. This is work that Keith Schilling at DNR did. So this is one of his papers. I should have had the reference here, but anyway. So what they showed, without going into a lot of details, is that they examined tile drain watersheds and non-tiled watersheds, and found that indeed tiled watershed have a simpler, fast way in which the flow recedes. So there is a very simple signature of tile drain watersheds that you can figure out. So now I won't go into the details of the model that we used using this particular attribute of the watershed. What I'll just say is that we were able to build a model that was able to predict stream flow at the outlet of a 700 kilometer square watershed, as well as the conventional models. While the conventional models needed softwares, ours was done on an Excel spreadsheet. So this is work that just got accepted. So then we said, well, this is stream flow. Can we go from here to say, well, what would nitrogen loads be? Can we link stream flow to nitrogen loads? Once again, we follow our pattern process pathway. So we look for patterns. In this case, we looked for patterns across large watersheds in the Mississippi Basin. So these are large meaning 200,000 to 800,000 square kilometers. And we said, what is the nitrogen load that is contributed by these watersheds? So here we plotted, so on the y-axis in these figures, you see nitrogen load. So this is mass of nitrogen that is discharged by that watershed per unit area, per unit time. And on the x-axis, what you see is the mean annual stream flow. So each of these different colors represents one watershed that you saw in the last page. And each data point is a particular year. Now think about this. 11 large catchments of the size 50,000 to 100,000 square kilometers, as diverse as they can be. However, see the amazing linearity between load and discharge. So what that says is basically load is equal to concentration times discharge. And the fact that you have this linearity, what that says is that the mean annual concentration of nitrogen does not change significantly from year to year. So from year to year, what changes a lot is the mean annual stream flow. So you see, for example, if you take any of these, right? So if you think the red data points, that changes from 0.1 meter per year to 0.6 or 0.7. So that's quite a bit because these are mean annual values. But the mean annual concentration doesn't change, so the mean annual load changes direct proportional to the mean annual flow. So what does that mean? What it means is now if I know what my stream flow is going to be next year, I have a fairly good first order estimate of what my mean annual nitrogen load is. So what does this concentration depend on? Well, it would depend upon land use. So if you have a lot of agriculture, that mean annual concentration would be greater. So here you see this kind of clustering behavior, right? You see there's one group which is kind of these values that have one value of concentration, and the other group that has another value of concentration. So you have these two values of concentration. Same pattern we actually also saw for phosphorus, and I'll come back to that in a bit. So let's take this message from this figure that the mean annual concentrations we are observing is not changing that much. So then we asked, well, just this is a curiosity side that is this unique to nitrate? Is there something about nitrate? Well, in order to ask that question, we selected 3 large basins, the Missouri, the Mississippi, and the Ohio, and we looked at a bunch of constituents. So you see these 3 are the 3 basins, and here we have nitrate, here we have total Kjeldahl nitrogen, and here we have ammonia. So on an average, you see this very strong linear relationship between load and discharge. You still keep seeing that. Scatter is a little bit much more for ammonia, but ammonia has other issues, so because it has other sources, so we won't go into that right now. Then we looked for phosphorus and silica. So this is total phosphorus, orthophosphate, silica. Once again, very strong linear relationship. The strongest, though, of course, is silica. Then we looked at carbon. So this is bicarbonate, dissolved organic carbon, and particulate. Once again, pretty linear relationships. So the relationship between load and discharge is linear, but the slope of that line is different from every watershed and constituent. So we wanted to say, well, what does that slope depend on? We wanted to explore that question a little bit further. So what we did here, we plotted the load of bicarbonate along the x-axis. So bicarbonate, because bicarbonate reacts relatively less in the system. And on the y-axis here, we plotted loads of nitrogen or phosphorus. And what we found is when we did that, so now we've taken all the watersheds together and we've plotted one constituent against another. We found that all the watershed collapsed into these single lines. So these slopes of these lines is a function of the reactivity of this particular constituent as a function of the reactivity of bicarbonate. Once again, this very unique pattern in nature. And we've not in this work, we are kind of at the stage we have found this pattern and we are asking why this pattern exists. We have not really used it in a model yet or delved further into it. Well, then we asked, well, is it about something about the Mississippi Basin that's created the pattern? Because for a long time we were thinking, well, maybe the tile drains too. So there was a colleague in Europe. We were talking to her and she said, well, I see the same thing. So this is hypoxia in the Baltic Sea. So she had data from a large number of countries around this area. We took her data and plotted them exactly the same way. And this is total nitrogen for Denmark, Estonia, Finland, Germany. So a whole range of European countries. And we see the same pattern. Their data set is smaller, so ours is about 30 years or so. This is about 10, 12 years worth of data. Once again, the same linearity between load and discharge. This intrigued us, and we were trying to find out. So whenever we see a pattern, our next thing along that line is we are looking for the process that contributes to the pattern, right? So process exploration is kind of then, to an extent, a bottom-up exploration. You need to know what the processes are. So we said, well, let's go at a much smaller scale. Let's go at the scale of a 500 kilometer square watershed. And at this watershed in Illinois, we had very good quality data. So when you're talking about the Mississippi Basin, water quality data is sparse data. Here, for example, we had daily data. So we took that data and we plotted, same graph, nitrogen load as a function of discharge. Once again, we see the linearity. Same pattern. Well, then at that site, interestingly, in addition to nitrate, we also had data for atrazine, which is a pesticide that's also applied to agricultural fields. Well, so we said, well, since we have it, let's also plot it like this. By then, we had gotten so much into plotting load discharge that whatever happened, we wanted to plot everything as load discharge. Well, so atrazine is not linear, right? So if you look at atrazine load versus discharge, there's quite a bit of scatter. I wouldn't call that linear. So that intrigued us. What is it about atrazine that creates this pattern, and what is it about nitrate that doesn't? What is the link between the two? So what is the difference between them? Because we thought that that would be a window for us to figure out why nitrate does what it does, or why phosphorus does what it does. Well, the difference, one of the big difference, is that atrazine has no internal source within the system, and atrazine has a very fast degradation rate. So atrazine is normally applied April, May, and within 4 or 5 months or so, you don't see atrazine anymore in your stream flow. So whatever atrazine was there, either it degraded or it went into inaccessible portions of the soil, and you see it no more. So the next year when you apply atrazine, you would see again atrazine, but between those 2 points you wouldn't, right? So it has a small half-life in the system, and it has no internal sources. Nitrate, on the other hand, has both external source, which is a fertilizer, but it also has internal sources, because nitrate is generated by mineralization of organic nitrogen in the system. So nitrate is, we call these exogenous and endogenous sources. So an exogenous constituent is one that's applied externally to the system, like atrazine. An endogenous constituent is the one that is generated within the system, like silica or calcium, that's weathering products, right? So those are pure endogenous constituents. Nitrate is like a hybrid. So it is externally applied, but there are also internal processes generating nitrate within the system. So based on this, we hypothesize that decades of fertilizer application have created this legacy mass of nitrogen within the system that acts as an internal load, as a buffer, and creates this effective biogeochemical stationarity. So what is effective biogeochemical stationarity? So stationarity is a concept that's used quite a bit in hydrology about systems that don't change in time, right? So we say, well, this is an example of biogeochemical stationarity because the concentration is not changing in time over the last 30 years. And the reason is, over the last 20, 30 years, the nitrogen that you have applied to the system has been converted to organic nitrogen, and that's just sitting there. So whatever differences you're making to your application today is not really affecting what you're seeing in the stream. That's the legacy of what happened 20, 30 years ago. So if you make any changes in land use practices, there is a chance you won't see any benefit. Depends on, if you do riparian zone changes, probably you would see it faster. So it depends how long it takes to flush the system clean of its memory. And we don't know that. For phosphorus, it's also true. So for phosphorus, and on this, a lot of work has been done in the Everglades in Florida, where they reduced phosphorus loads from the pastures. And what they found was that did nothing to the phosphorus loads that they were seeing. Because once you reduce your input, the sediments which had accumulated phosphorus over decades was now the internal source of phosphorus. So this is a great example of human impact, how we have created these man-made systems that act now as sources. So taking this a little bit further, I said this was our hypothesis, right? We have not really proven it. But what we wanted to do is kind of look at more endogenous constituents and see if they really do show this biogeochemical stationarity that we are talking about, or in other words, we also call it the chemostatic response. A chemostatic response means the concentration is not changing with time. So this is data from LTER sites. So LTER is the long-term ecological research site which is funded, and there are a few of these sites along US which have very high quality data. So we took data from those sites and we plotted the same thing. So this on the right is the load-discharge relationship for calcium, sodium and sulfate, and on here we have plotted concentration against discharge. So you see there is pretty strong linear relationship between load and discharge, and much stronger than what you saw before for nitrate, right? So if you think about these cascade of constituents, at one end you have endogenous, which are very, very chemostatic or stationary. The other end is atrazine, which is completely non-stationary, or it's varying from year to year. And nitrate is somewhere in between, where it is actually an exogenous constituent in terms of fertilizer, but it is behaving like an endogenous constituent because of human impact. So another example, this is just another paper, a large number of sites were looked at, and generally what was observed that geogenic constituent or endogenous constituents showed this chemostatic response. So what does that mean? Two things, one good and one bad. So I like the bad things first. What it means is that we've created a persistent legacy source of these constituents in our watershed. So if we want to do restoration, if we are looking for, we need to think about both short-term and long-term impacts of restoration. If you are thinking of short-term impacts in terms of improving our stream water quality or Gulf of Mexico hypoxia, changing land use wouldn't do anything. What we need to do is more control at point, meaning creating wetlands that actually divert the water and treat it, or treating it near the Gulf. So there are different kinds of pollution abatement strategies which are more at where the pollution is occurring. So those are short-term measures that need to be taken. Of course, we don't want to transfer this legacy of contamination to the next generation. So then we need to focus on long-term measure, land use change, better use of fertilizers, because as I was showing in one of those, more than 40–50% of the nitrogen fertilizer that is applied to the soil is leached. So we haven't really figured out how best to use it. It's more so in the developing countries, but more and more research is done on that, and there are ways of exploring how we can reduce that leaching. So we need a balance of those two kinds of approaches. And if we want to understand impacts, we need to figure out how long it takes for a particular constituent to travel through the watershed. What is its reactivity within the watersheds? If we understand that, then we'll be good. The good thing for us modelers is that this is a pattern that we have found, and we can explore this pattern to develop these models across scales, to go from a single tile to upscale it to predict what is happening at the watershed outlet. So for example, if we have climate models that tell us how much the runoff is changing, we can use that to predict what the load is changing. Of course, it's not as easy as that. There are a couple more steps to it. For now, we've just found the pattern, and we are looking for ways to go from the pattern to the process and prediction stage. But this is where we are now. So I promised that I would come back to my last slide. So my title was Exploring Emergent Hydrologic and Biogeochemical Patterns in Catchments at Multiple Scales. So the linear LQ relationship is an emergent biogeochemical pattern. The tile drain watersheds and the way it simplifies the hydrology is an emergent hydrologic pattern. So we are exploring that right now at multiple scales with the overall goal of developing robust but simple models, so that ultimately those can be coupled with socioeconomic models, which is what I would like to do in the future, to say what kind of farmer decisions are needed to be taken and what impacts you would see later. So with that, I would like to thank you again for being here. It was great coming here and giving this talk. Thank you. No, I do want to. So I've been, as I was saying, so most of my work that I've shown here is work that I was doing while doing my postdoc. So, and I just getting more into the groups over here and eventually do want to go there. But we need to first figure out to an extent like this pattern and how that relates before going to that stage. Well, for the long term, you don't really want to be loading your system anyway. You want to also mitigate that and not have to, because wetlands also, so in Florida you see these examples of stormwater treatment areas, which are these wetlands that were created to reduce the loads. Well, what's happening now is that they have become overloaded, and so they are not working. They are becoming sources themselves, actually. So that's true for phosphorus, not that much for nitrogen. But so you need to be doing both. So water quality measurements are the data that I have shown is large scale data. So this is collected by USGS. And this, I would say, is about, at the max, you would get 8-10 data points a year. Well, sometimes more. So biweekly or monthly sampling is what they do. So the Little Vermilion data set, the Illinois watershed, that actually has hourly data. So it depends, and a lot of work, effort, money is now going into having these automated sensors. They are very expensive, but then you have this entire time profile and you understand a lot what's going on in these systems. But then you have this huge spatial extent that you need to figure out. So I would say the new automated systems do give you, so going out and collecting samples is one, you have to be very careful that it's not biased sampling, because a lot of times you don't go out when there is a storm. Graduate students do, they have to, but normally people don't. And so I would say in terms of accuracy, and if you have calibrated your sensor better, it is better. But a sensor, a nitrate sensor, just as an example, costs $15K. So how many of those do you put in your watershed, right? So what I believe in, honestly, is that you need both. So you need to integrate this kind of sampling, and there's more innovative samplers that are coming up, and I'm interested in work. I'm actually working on one of those where these are more crude. So you put them and they give you the mass load per event. They're not like every minute or every hour, but then you get an idea of in space where your contaminants are coming from. So you need a mixture of all these. So the Illinois data set that we used right now to do the analysis was daily data. They collected 15-minute data, but we haven't processed that data set because it's just massive 10 years, 15-minute data set. We haven't processed that yet, so that's still there. But they did ISCO samplers. So ISCO samplers, you can set it to collect data at any interval that you want, and then you collect it over a storm period. So you have these bottles that collect samples every hour or 15 minutes, whatever resolution, and then you have somebody go out and pick them, change the bottles, and then you have another round. So that's, the nitrate sensors are the most sophisticated, that second level of sophistication, and then you go with what's actually done most cases, that you go and take a sample during an event. Or so, so this one had the ISCO samplers.
Okay, that was for an event?
No, that was 10 years.
10 years?
Hourly data. That's what they have. Yeah, it's a very beautiful data set, and we've done a lot of other kinds of analysis with that data set. It's rare to find that good a data set.
So yes. What were you expecting to find before doing the analysis with like the how do you call that, chemostatic behavior? You didn't have any idea what's going to happen? Or?
No, not really. What we were looking for is, well, what do the loads depend on? So it was pretty, so when you go looking for patterns, it's kind of difficult because you don't know exactly which you're searching for, but you're looking at these systems and you're looking for patterns. And I was describing this to a graduate student the other day, is that if you look too closely, you don't see the pattern because there's just some noise in natural system data. So you have to be looking at it a little bit far away to be seeing the pattern, kind of like those paintings where you need to be a little far to see the pattern. But at the same time, if you're too far apart, then you get into your own dream world and what you're seeing is not really true. So you have to play continuously this game of going a little bit away and looking for that pattern. So we didn't really search for any particular pattern. We said, what does the load depend on? plot it against area, plot it against discharge, what are we? And we said, well, if we can somehow find any kind of relationship between load and discharge, that will be helpful. We were not necessarily expecting a linear relationship. We were definitely expecting more nonlinear, because if you look at local CQ patterns and hysteresis work that has been done based on that, we were expecting a nonlinear relationship. But this is the idea of emergent pattern, right? Some things that you see at the small scale, small spatial and temporal scale is not what emerges out of your system.
So, but that's the idea is if you have the discharge, you can predict the load?
Mm-hmm. Yes. If you have the discharge, and actually I have not shown that much here, if you have the discharge and if you know the land use, so the slope of that line we found to be pretty well correlated with percent land under corn. Right? So if you have more land under corn, it's generating more nitrogen. So you have this mean annual concentration is more. So if you know the land use, which you do, and if you know the discharge, which is relatively easier to predict than the contaminants, then you know the load.
Next year.
Right. So the thing that intrigued us and kind of made us think twice is if you think about these watersheds at these large scales, there's been quite a lot of conservation activities going on in terms of buffer strips, in terms of why aren't we seeing that signature here? And the answer is you would see that signature at the scale of a 10 kilometer square watershed where we are putting that. But at the large scale, for you to see that signature, it would take a relatively long period of time. So it's the time lag and it's the space and time that you have to play around with to be able to see that pattern. So if you have a riparian buffer, you would see something, but then maybe that signal is diluted because as you're going down gradient, there are other sources that are picked in. So it's a balancing game, and don't know really how that works, but ultimately all that doesn't change this, so which is what intrigued us, still intriguing us. Thank you.